Today I'm going to talk about magnitude channel effects. So let's start. First, let's talk about MOSFET capacitance. When we make one MOSFET in here, we overlap many materials on the MOSFET. So like this is the gate and oxide, and this is the poly-N-type, and this is the substrate. So many materials overlap each other. So in this situation, every junction has a capacitance. So we should know about the characteristic of capacitance, and we use it too. So in this case, in this part, and there are four capacitance in this part. So if we calculate every capacitance and then plot the graph, we can obtain this graph. So there are many capacitance in here. However, finally we should see only the oxide capacitance, because this is the most influenced capacitance in this case. So every part of this capacitance graph, it means accumulation part, inversion part, and depletion part. So after we look this graph, and we can divide the characteristic of state, the MOSFET state. And then let's talk about subthreshold swing. This is a very important concept of driving the device current. The slope of this graph means subthreshold voltage, subthreshold swing. So if the slope is lower, like this way or this way, if there are any changes about this graph, like off state and on state, that device will work very bad. So we should make a higher slope for device working. So this is the very important concept. So if we can draw this graph based on the equation. So in room temperature, the limit of subthreshold swing is 60 millivoltage. So we cannot make lower subthreshold swing than 60 millivolt. So we should make a lower subthreshold swing upper than 60 millivolt. And then let's talk about the short channel effect. This is the punch through effect. So you can see this graph. This graph means the how current flow. Actually, in this part, the current not flow in here, but after the voltage, we put some voltage, the current will flow a lot. However, in this part, in this graph, we don't put some voltage in this part, in the left side of graph, but current flow a lot. So this means device cannot switch its state like off and on. So it means also that device cannot work very well, because it cannot work like switch. So this is very poor device condition. So we should change this. We should solve this problem. So switching concept is very important for transistor because we should put some voltage and then we should put some voltage to control the current of device. However, in this case, we cannot control the device, so we should solve this problem. And then this is the solutions of the punch-through problem. First, increase substrate doping. And then second, silicon on insulator or ultra thin body SOI. So we use these two materials to solve this problem. And then lastly, strength relaxed buffers. So we should use those three solutions to solve the punch-through problem. And until now, we make a new solution to more effective solution to solve the punch-through problem. And then let's talk about Review2 roll-off. This is the gate and channel length graph. The left graph means enough gate length. This device has enough gate length, but this device doesn't have enough gate length, very short gate length. So in this, because of that gate length, the source and drain, the depletion region of source and drain influence each other, so it makes a Review2 roll-off. So if the gate length gonna be smaller, the Review2 also gonna be smaller than before. So if because of the gate length lowering, we make a Review2 then about the calculate. However, based on calculation, but if this problem happened, we cannot control the Review2, and so if we put some voltage, but it works very well, but very bad because we make a specific Review2 before, but because of the gate length, we cannot use that Review2. So this is very important problem, and we should solve this problem too. So let's more talk about the gate length and channel length problem. DIBL is drain-induced barrier lowering. So at the long channel, we put some voltage to the drain. The drain energy band will be lower than before, like this way. So it gonna be lower and lower to this side. However, the first barrier cannot be changed, cannot be influenced by this drain voltage because it is so long. So the barrier of the source and channel will not be changed. However, at the short channel, if we put some voltage to the drain, this energy band will be lower like this way. However, it is too short, so the barrier of the source and channel will be lower together. So it means more electron, more carrier can be moved to the channel, and that also means we cannot control the specific carriers. So So we should also solve this problem too. And GIDL means gate-induced drain leakage. So I said transistor also works like switch. So we should control the off state and on state every time. But when the GIDL happened, at the off state, the current flow like on state. So it is very bad situation because we want to control that device to off state, but because of the GIDL, the current will flow and it influence to the device that works very bad. So yes, and then how that GIDL happened, we should, if we make a device that gate and drain overlap in here, so in this part, if we put some heavily doped in the drain, it makes a depletion region and overlap the gate. So this depletion region make some problems. So in this energy band diagram, this depletion regions make in here, and then energy band diagram also changed like this. So the carrier in the left side tunneling start to tunneling the right side. So this means the leakage current. So this situation influences the leakage current, and it makes the device work worse than before. So we should check the GIDL that happened in the device, and if the GIDL happened, we should change some condition of device and then solve this problem. So today we talk about the short channel effect. So thank you for watching my video. Bye.